Hello everybody, this is Professor Iris Miano giving you your week 10, day 19, if I'm not mistaken, lecture video concerning the very first two sections in chapter 7 that we're going to cover. We're going to skip section 7.1 because it's all about proportions, giving you an introduction to proportions, and I'm going to assume that since everybody has at least an working elementary level knowledge of algebra, that we know what a proportion is, how to set them up, how to use them, how to solve for an unknown, all of those things. Certainly in the midst of talking about similar polygons, we will go into the algebra in some detail regarding proportions, but if you ever need more detail on anything algebra related, or well, anything in this class, you need only ask during our class discussion sessions. So we're going to introduce what it means for polygons to be similar, and we're going to transfer that specifically into learning how to prove that triangles are similar in section 7.3. And here we go. So polygon similarity, which is often designated by this symbol, which we have already been introduced to. Remember way back in the day in chapter 2 when we were first starting this class, and we had this symbol, the squiggle line, called a tilde, representing something very specific within our logic component? Yes, so the symbol is coming at us again, but it has a different context, and it's going to be shorthand for the term similarity, okay? Whereas it was the negation symbol in our symbolic context, here it has a different context, being a mathematical shorthand for the word similarity. So let's just make sure we transfer over what we need to. I gotta answer a text message. I'm just gonna pause the video just ever so briefly. Just a moment, guys. Okay, and I'm back. I don't think that is much of an interruption for you guys. Let's continue. Polygons are defined as being similar if and only if. Now this if with two F's is not a typo, it's mathematical shorthand for the phrase if and only if two conditions are satisfied. So the one condition is that all pairs of corresponding angles are congruent. So that's a leftover from polygon congruency, right? Like all of the corresponding angles had to be congruent and all corresponding sides had to be congruent for polygon, and more specifically triangle congruency. But now we're in similarity, which doesn't have to be as stringent as far as the relationships of the side lengths are concerned. And that brings us into our second condition, in which all pairs of corresponding side lengths are proportional. So please recall from your algebra days that proportionality, a proportion in general, is an equality that occurs between two ratios, okay? Or to, what's the other word? Ratio? Rates, if you have different units in numerator and denominator, but they have to match across the equal sign. So that's not something that we dive too deep into in this class, so it's not something we're going to dwell on too much. Okay, but anyway, the thing that we want to keep straight here is what a proportion is, how to set up a proportion. And proportions can be set up in a string, and by that I mean it could have multiple equal signs in play. Now when you're asked to solve for a particular unknown value, you have to drop, down all of the extra ratios in a string proportion such that you just have two ratios set equal to each other in order to be able to do the cross product that lends itself to solving for an unknown. So if all of that I just said was gobbledygook nonsense, that you're like, I don't know what you're saying, do not worry, I have examples coming that are going to highlight the details associated with solving proportions that contain an unknown. Okay, so we're going to dive straight into an example right away, and here it is. Let's say we have these two triangles that appear to be sharing a vertex K. The edges of these two triangles touch right here, okay? And that these triangles HJK, which is this one, HJK, the smaller of the two triangles, right? Let's say it's similar to triangle FGK. And one thing that I want to point out now that we're in the similarity section, or sections, there's a couple of sections dedicated to similarity throughout this chapter. The names of the triangles, the order in which the vertices are placed in the name, like the fact that this first triangle's name is HJK instead of JKH or any other combination of letters, has a lot more meaning now, because when you are linking two triangles or polygons, for that matter, together via similarity, which is this tilde right here, then the order of the vertices matter as far as linking them up in the relationship between corresponding vertices, okay? So that means that vertex H and vertex F have this relationship in that if you can call them just angle H and F, which we certainly can in these two triangles here, we could just call this H, angle H, that is, and angle F, because there's no other, edges and angles that are formed besides this interior one, right? So we could say that angle H and angle F, since they are the first letters in each of the triangle names within the similarity relationship that's presented, that they are congruent to each other. They are corresponding angles among similar triangles. Okay, so that'll become more, what's the word I'm looking for, evident as we progress. Now, we could say the same is true for J and G among the two triangles. Here is angle J, here's angle G. They correspond because they're each of the second letter in the triangle names among the triangles that are similar. Now notice that the last letter for both of the triangles is K. Now can you say angle K is congruent to itself? Well, of course, sure you could, but here, since K, this vertex, is the intersection of two lines and that technically four angles are being formed, you really have to have the three-letter name of the angle, the interior angle for the triangle, in order to effectively name it, to make it super clear which angle you're referring to. So we would say angle HKJ, therefore, is congruent to angle GKF, if you like. Okay, cool. Great. Now notice, so that's just a little bit of an overview of like some of the things that we get to take into account by virtue of taking that first condition that was presented in the definition of polygon similarity. Corresponding angles are congruent. Now, corresponding side lengths are merely proportional, and you'll notice that some of these side lengths are given to us. That HK, that's this distance right here, is supposed to be of length 6 units, unnamed units. KF, which is this length right here, is going to be length 8. FG, so F to G is of length 5. So we want to use that information, noting that the triangles are similar. Exercise our notion of the side lengths being proportional to each other using these lengths to find HJ, okay? Now please note that this drawing is not to scale, and it becomes maybe super evident once I put the numbers in here, like if you were to actually physically measure HJ versus FG. Yeah, that would be not making much sense. But anyway, we want to just take these numbers at face value and understand that we want to set up a proportion in order to determine this value of this length HJ. That's this length from here to here. Okay, cool. So here is the string proportion that we get to set up for these two similar triangles by virtue of understanding the second condition in the definition of similar polygons. It's this. Okay, so take your letters that are given to you in the order that it's given to you for the triangle names. This is a lot of information if you know how to use it. So every two letters, every combination of two letters, you get to set up a proportion of side lengths, right, in a ratio and ratio and ratio. There's going to be 3 different ratios going on because each triangle has 3 edges, right? So each edge for one triangle corresponds to another edge in the other triangle. Now, which edges correspond? The letters order gives you clues, okay? So HJ, the first 2 letters in the first triangle named, corresponds to FG, the first two letters in the second triangle. So that's why HJ over FG is the first ratio in the string proportion, okay? JK being the last two letters in the triangle name, the first triangle that's mentioned, corresponds to GK. You see that? The last two letters in the other, the second triangle. And lastly, take the first and last HK, and then correspond that to FK or KF. I switched it to KF because that was already established as being the name of one of the given lengths of the second triangle. Okay, so KF, FK, technically it doesn't matter in which order you name vertices or endpoints when you're talking about a line segment. So, you know, you could switch them as needed to keep with already established conventions, okay? So here is our string proportion. And remember, this came about from understanding that these triangles are stated as being similar by virtue of this tilde being in play with the connecting the two triangles, and understanding what a proportion is. So take all of the corresponding side lengths, use the order of the vertices in the triangle names as your guide, and set up this string proportion. Okay, now we can take the given values and replace them with the edges, the measures of each edge that are known to us, like so, okay? So I'm just going to take, because, HK, excuse me, and KF were given to me, so that's the 6 over 8. And then HJ over FG was the other thing that was given to me. So I'm going to go ahead and take those two ratios and set them equal to each other. Notice that JK over GK, while it's true that those two lengths are in ratio and part of the string proportion, they don't help me in trying to solve for HJ, which is ultimately my goal in this example, okay? So I dropped the middle ratio and set the other two ratios on the left and the right ratios equal to each other directly while plugging in the given values, okay? Now let's use the cross product in order to solve this proportion, and then we're done. Okay, so notice that the cross product would yield 30, which is 5 times 6 on this side, times HJ times 8. So I put 8 times HJ with a raised dot in between. Now I simply need to use the division property of equality to divide both sides by 8, and that will give me HJ has a length of 3.75. Yep, that's true. 8 does not divide evenly into the 30, so I'm going to get a decimal final answer, and that is okay, all right? And definitely this is something that you're expected to be able to do, you know, by hand, because we're not, you know, trying to use calculators in this class. However, for relatively simple things like this, it would be fine if you just quickly used a calculator during homework. I can give you some leeway there, but just know that you're expected not to use a calculator on the exam. You won't need to. Everything's going to divide real nice when problems like this come up in an exam setting, okay? Cool. So, just as a quick recap before we move forward in some theorems that are coming our way, we had similar polygons, triangles specifically, that were noted, some side lengths. We set up a string proportion to find the value of a missing side length, okay? And use the cross product, you know, put our algebra hat on in order to eventually find that unknown value. Cool. All right, what's next? Let's go ahead and go forward. Oh, here's another example. And we're going to have similar quadrilaterals given to us. So quadrilateral ABCD is similar to quadrilateral HJKL. Okay, and we don't know what kind of quadrilaterals they are. We've been introduced to all the different kinds that we care about in this class, which were, if you recall, parallelograms, rhombus, kite, square, and rectangle. So those are the possible quadrilaterals that the ABCD and similar quadrilateral HJKL could be. We're given some information about some of the angle measures and between the two quadrilaterals, and we want to determine what types of quadrilaterals ABCD and HJKL could be. Okay, so think about all the different quadrilaterals that were presented in Chapter 6. Take a moment, maybe even press pause on this video, and take a moment to maybe draw a picture and say to yourself, what can I determine based on the given information and some just a general picture that I could draw? What kind of quadrilaterals do I think I have here? Doody, doody. Okay, I'm going to go ahead and just tell you what they are. They're parallelograms. And how do we know this? Okay, so I'm going to do a little bit of cheating and draw my quadrilaterals for this illustration as parallelograms. And so let's just say that I have quadrilaterals A, B, C, D, H, J, K, L, right? And so notice that corresponding vertices are in the same general places among the two quadrilaterals. And, you know, spoiler alert, they look like parallelograms, but let's put the information together in order to arrive there. If you weren't able to guess this ahead of time, how would we determine this? Well, you would want to put the angle measures that are given to you, right, in the corresponding places. Oh yeah, sorry, and before I get too deep into this, because the quadrilaterals were similar to each other, I get to say that angles that correspond are congruent to each other, and the order of the vertices is your clue, okay? So I know that angle A, since it's the first letter in quadrilateral ABCD, has to correspond and is therefore congruent to angle H, and so on and so forth. Furthermore, the measure of angles A, K, and B were given, so go ahead and put those in the interior of the angles in question. And since we know that angle C has to be congruent to angle K. So we know C is going to be 70 degrees, right? And then J has to be 110 degrees because it corresponds to angle B and is congruent to angle B. And angles A and H have to be congruent because they correspond. Now that you have quadrilaterals, like 3 out of the 4 angle measurements are known, you can use what you know about the interior angle sum of any quadrilateral. It's going to be 360 degrees. You can use the formula that was given in chapter 5. So, what was that? Was it chapter 6 or 5? Or 4? No, it's 4.5 rather. It was chapter 4, section 5 that gave us that formula. For the interior angle sum of any polygon, or, you know, there was a very offhanded theorem that was presented just in, in the textbook that said the interior angle sum of any quadrilateral is 360 degrees. I'm rambling, so let's just go ahead and move forward and say we know that there are only 110 degrees left for angle D, and so similarly angle L has to be that same measure. And notice that in opposite positions, the angle measures are the same for both opposite angles within each individual polygon. So that alone tells us that we have parallelograms, okay? Cool. Moving on to the next example. Let's say that these two triangles ADE, which I would call the interior smaller triangle, and the exterior or main triangle ABC, are similar to each other. All right, so we know some things about corresponding angle measures need to be congruent, and corresponding side lengths are proportional. So we're going to use that that condition heavily, along with these given lengths and the fact that these two lengths DB and BC are said to be equal to each other in order to find the length of AB. So here we go. Let's first recognize and introduce some new notation. New to us, well, not new to us, but new context here. So the textbook introduces this 2-pointed arrow to mean corresponds to, which is to say that a line segment AD, right, corresponds to line segment AB. And notice that AD and AB are the first 2 letters in the names of the triangles. So we know that we can set up a string proportion in which AD and AB are in ratio to one another. Similarly, this is true for AE and AC and DE and BC. if you recall from chapter 2, this symbol, this double-sided arrow, used to mean a biconditional relationship between two statement components. So here, yet again, in the same chapter, or section rather, we have 2 bits of old notation that have new meaning for us. So it's our job to make that adjustment, and it might be a little bit hard at first, so just try your best. Okay, so when you see this formally a biconditional symbol, the double direction arrow, it means corresponds to, okay? And that allows us to set up the string proportion like we did in that very first example. So what elements are known to us? Well, DE is known, so we'll put a 5 right here, AD is known, we'll put an 8 right there, and then we'll probably knock out this middle ratio, right? Because it doesn't have anything to do with what we're trying to find here, the value of AB. Okay, so let's see what we have here. Okay, so we have AD is 8, and then AB, we do not know the value of AB, but we know that a portion of it, this value of 8 associated with this portion of AB happens to be known to us in the form of AD's length of 8. DE is also given to us, that's this one right here, which is 5. Okay, so notice that AE over AC is completely useless to us at this moment. That's not uncommon. It's good to set up the entire string proportion, but recognize that one of the ratios is going to be not useful to you in regard to finding some unknown value. Another thing that we'll want to notice here is that we have this, so we're eventually going to knock this middle ratio out, and we have this unknown and then this other unknown BC. Okay, so having one equation with 2 unknowns is problematic in being able to find the value of any particular unknown. But I want you to recognize something that's been given to us right here. The last piece of given information is that DB is actually equal to BC. So watch what I'm about to do here. Focus right here on BC as I click forward. Watch this. Ooh, yeah, see? BC and DB are the same value, so I can substitute one for the other, right? Because of this right here. Everyone cool with that? All right, so now what I'm going to do is I'm going to clear everything on the page because I have a lot more calculation to do, but I'm going to pick up where I left off right here. I'm going to take out the AE over AC ratio and continue with the rest of my work that I need to do, because I'm going to need to do some cross product. And doing this part of the cross product where I'm going to multiply 5 times the quantity 8 plus dB, that's a little bit, challenging algebraically. Just remember that you're going to need to distribute that 5 over the 8 plus dB quantity, and then you're good to go. Okay, so here's what it looks like to distribute. And I will combine like terms by subtracting 5 dBs from both sides, okay? And so I'll get 40 equals 3 dBs. I need to divide both sides by 3, and I will get 40 over 3. Ew, I know, it's not a number that divides nicely, but it's what we have. And so we need to now take this value and do something with it, because dB is not at what we asked for to find, right? We were trying to find the value of AB. So then we need to take this 40 over 3, add 8 to it, the value of AD's length, and then that'll give us 64 over 3, and I did a little bit of algebra here that is not present on the page. I'll describe it to you somewhat, but we could always do this as a problem demonstration in class if anyone needs a little bit more detail. 8 could be written as a fraction, 8 over 1, and then built up to have a common denominator with this 40/3. By that I mean we can multiply numerator and denominator of 8 over 1 by 3 and get 24 over 3. So what I'm saying is 8 is equal to 24 over 3. Add 24 over 3 to 40 over 3, and that's how I get 64 over 3. You can do the long division, or, I would allow for some calculator use on this, sure, why not, for the purposes of getting through your homework faster. And you will get that 64 divided by 3 is 21.33333 forever. So throw a vinculum over that 3 to indicate that that 3 does indeed repeat to infinitum. Okay, great. fun. So, as you can see with some of the similar polygon stuff, when you're dealing with proportional side lengths, you are going to need to do some algebra, and that's because of the proportional nature of these side length relationships among the similar polygons. You can't have one without the other. So let me know if we need some more algebra review in class. I'm happy to fill in the details there, give you some more stuff if we want. Okay, let's dive into the next section here. So that was the end of 7.2, similar polygons. So we introduced this idea of what it means to be similar, but now we're going to learn how to prove that specifically triangles are similar. And there's going to be 3 more 3-letter codes, 2 5-letter codes. You got so used to CPCTC, didn't you? And now we have 2 more 5-letter codes just to make things interesting / more confusing for you guys. Okay, now all of the 3-letter codes that you're going to learn today are for similarity. Okay, these are not for triangle congruency. We already went through all of those way back in chapter 5, section 1. But yeah, now we're in triangle similarity section, so it's like gonna feel very familiar, but it's a totally different concept where you have triangles that are the same general shape but different sizes. Okay, so what is AAA? Now, if you recall from 5.1, this was a no-no for trying to prove triangles congruent, but it's totally fine for proving triangles similar because it just really outlines that first condition in the polygon similarity definition, if you recall from 7.2, which is to say that all corresponding angles among 2 similar triangles are congruent. So if you can show that all 3 of them are congruent to each other, then you can prove that the triangles are similar. Like so, let's say you were given triangles ABC and DEF, and if it can be shown or it was given to you that all 3 of those angles among the 2 triangles correspond to one another, notice the arcs, right, among the 2 triangles and this series of congruencies that are mentioned, then the triangles are similar. Okay, if you can establish all the angles have that relationship, then that's one way you can prove triangles similar. But guess what, guys? It actually turns out you do not even need all 3 of the triangles to be explicitly shown to be congruent to each other. Actually, you only need to do 2. So here is the corollary. It's a corollary is a subtheorem that's connected to a main theorem, and so this one is, or in this case, it's connected to a postulate. And this one is just saying, hey, just kidding, it turns out that you only need 2 angles to correspond and therefore be congruent among 2 triangles in order for the triangles to be similar. And why is that, do you think? Well, it turns out that it's very much related to that one theorem that was presented, ages ago, that stated that if you have, among 2 triangles, if you show that 2 angles are congruent to each other among the 2 triangles, then the third ones are also congruent to each other. If you recall that one, then that's what lends this particular corollary to be also true. Okay, so if you can establish that at least 2 pairs of angles within 2 triangles are congruent, then that's triangle similarity is established. That's all you need. What else? How else could you prove triangles similar? Well, before we get into that, there's a couple more 3-letter codes coming with little tildes after them to indicate similarity. But let's first dive into our next 2 new 5-letter codes. Remember CPCTC? If you recall, CPCTC, not this one, stood for corresponding parts of congruent triangles are congruent. Now we have a 5-letter code, CSSTP, which stands for corresponding sides of similar triangles are proportional. So if you recall, that was the second named condition in, associated with the second condition for the definition of similar polygons. So let's say that we have 2 triangles that are similar. What can you conclude based on CSSTP? You can conclude that any of the 3 corresponding edges are in proportion or in ratio with their corresponding edges in the other triangle. So basically you can conclude this string proportion, okay? That's the thing that gets to be said if triangles are similar to each other. You can CSSTP your way into making this conclusion, or any piece of it. So you don't necessarily have to state all three of these ratios being equal. You can have any two of the ratios equal to each other and use CSSTP as justification. So there's another 5-letter code, which kind of relates to that very first condition that was mentioned in the definition of polygon similarity, and it's that corresponding angles of similar triangles are congruent. CASTC. The first, letter of each non-trivial word in this sentence is the acronym. So what does that mean? If these two triangles, ABC and DEF, are similar, then we can make these series of congruency statements of corresponding angles. And how do you know which angles correspond? Remember, look to the order of the 3-letter codes. A is the first letter in the first triangle's name, D is the first letter in the second triangle's name, so that means angles A and D have to be congruent to each other, and so on and so forth. Okay? Cool, moving on. So, this is extending the proportionality of altitudes for similar triangles. So let's say you have two triangles and they're similar. You added some altitudes to them. So sorry, before we add the altitudes, because the triangles are similar, one thing that you can conclude from CSSTP is that all of the corresponding edges are proportional, i.e. you can make the string proportion statement. So throw altitudes in the mix. For triangle ABC, the altitude is presented here as line segment AX. The altitude for triangle DEF is line segment DY. They are also in proportion with all of the corresponding side lengths as well. Okay, so that's the thing you get to conclude from this particular theorem. All right, hopefully that's sufficient, but if we need to discuss this more, please let me know in class. So now we have a 3-letter code that's very familiar to us, right? But notice the incorporation of the tilde afterwards. So this is categorized as side angle side similarity, which is to say that if you have two triangles such that two sets of side lengths are in proportion to each other, so you just have AB is proportional to DE, and CA is proportional to FD, right? So those side lengths that were mentioned here have this included angles A and D that are congruent to each other, right? So all of those elements, or something similar, if they are in play among two triangles, then you can use SAS similarity to say that the two triangles are similar, okay? Because we have sides proportional and an included angle. Side, angle, side, side, angle, side. But since it's proportionality is the relationship between the lengths and not congruency, it's a similarity 3-letter code. So that's why it's SAS similarity. So hopefully that's all very clear to everybody. We have another similarity 3-letter code, side, 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 which is to say that if you have two triangles and you establish the string proportion for all corresponding side lengths, that's another way that you can conclude that the two triangles are similar to each other. Okay? Great. Now let's see. I think, there's one more theorem. It's a kind of a subordinate theorem, a lemma. It is kind of like a subtheorem, kind of similar to the way corollary is a subtheorem, but corollaries are always linked to a main theorem, whereas lemmas are kind of standalone, but they are considered subtheorems. It's a little nuanced detail. You guys don't need to worry about that. Just consider it to be a theorem. And it states, if a line segment divides two sides of a triangle proportionally, then this line segment is parallel to the third side of the triangle. So remember we had that other, I think it was also a lemma, that had us taking a triangle and connecting the midpoint of two of the edges and then making conclusions about the third edge being parallel to that midpoint connection line segment, and also twice the length. So we have a similar kind of relationship here where we just let this YZ, right? It's in proportion to that third length, right? And therefore we can conclude that the two lines, the one that was drawn inside of the triangle and the third line out, are parallel to each other. So as long as there's a proportionality relationship here, then the lines are parallel. So this is another way now, hearkening back to some chapter 4 stuff where we're getting really into proving lines parallel. This is another way that you can prove lines parallel if you happen to have this particular type of triangle scenario in play. Okay, so let's go ahead and write a paragraph proof as our closing example here. So I want to say a couple of things about this. Now, the only way that we have written paragraph proofs so far in this class have been using the indirect method. So, spoiler alert, surprise, surprise, writing a paragraph proof does not mean that you have to use the indirect method. The indirect method, on the other hand, always is done using a paragraph proof. Like, the style of writing for using the indirect method is always paragraph proof, but that doesn't mean that paragraph proofs always use the indirect method. You guys see that? The converse is not true here as far as the relationship between paragraph proofs and the indirect method, okay? So just to be clear, one more time before we start this last example, all utilizations of the indirect method require, as its methodology, the way that you write indirect method proofs is always using paragraph proofs. However, paragraphs proofs as a method is not always going to use the indirect method, okay? Cool. So let's go ahead and write this formal proof in a paragraph style. Okay, so please note what you've been given. You've been given this figure. You've been given that RS and AB are perpendicular to each other. And notice the incorporation of these boxes. That means that right angles are already, in play right here, right? Similarly, CB is perpendicular to AC, okay? And we're trying to prove that triangle's BSR. So BSR is the interior smaller triangle, and BCA is the main exterior triangle, so to speak, okay? Cool. So always start with what you're given, whether it's a chart style proof or a paragraph style proof, yes. So we're going to say since these collections of lines are perpendicular to each other, that means that angle C and angle RSB are congruent to each other, since perpendicular lines form right angles and all right angles are congruent. So notice that in this very kind of a run-on sentence, it's a little bit of a run-on, this isn't an English class, I have taken the given information and drawn a conclusion and justified it using or the definition of perpendicular lines. Sorry, I'm using two theorems, not the definition of perpendicular lines, but a theorem associated with perpendicular lines that perpendicular lines form right angles and that all right angles are congruent. So that's two separate theorems that I use to justify this claim right here about angles C and RSB being congruent. Angle C and angle RSB are two separate angles. What I mean to say is that they're in two separate triangles, okay? The two triangles that I'm trying to prove are similar. So far we have one pair of corresponding congruent angles. All I need to do now, if, the given information and or figure lends itself to the following, is show one more pair of corresponding congruent angles among the two triangles. Watch how I do it here. Then I notice that B, this angle right here, is the tip of the little triangle and the big triangle at the same time. So it's congruent to itself via identity, and I'm writing this out in English. I hope that's okay for you guys. And you could certainly use a symbology instead, saying since angle B is congruent to angle B. You could do that if you wanted to. I'm just saying using English, it's congruent to itself, and I'm using identity to justify that. Then, and I'll put a couple of arcs in there, to add to my figure. Then I have established AA, angle, similarity, right? That's the minimum that you need to establish in order to be able to state that the two triangles are similar. And there you have it. Here is my very short 2-sentence long proof, paragraph proof. Now, my sentences are a little bit of run-ons. I guess I would definitely admit that. So if you were to rewrite this or write this in your own style, kind of breaking the information up into more sentences, oh, beautiful. I invite you to do so. I think that would be good practice for developing your own style with these types of things. Definitely give that a try. And if you're just like, no, I need some more, study before I even try to write these down myself, by all means, write this down word for word as practice as well. Okay, cool. Here is the homework set that I want you guys to tackle. If any of these problems are strange and need a little bit more explanation, that's what our class time is associated with. And anything that was presented in this lecture video, we could certainly redo or give some more details to. I'd be delighted. All you need to do is ask. So I will see you soon for that. I look forward to it very much. Let me know what else I could do for you in regard to this material. Okay, bye everybody.